go. All right, so final exam review, and then I got to move you guys over to, no, I got to move you over to this other screen. Okay. So I can start. Come on. All right, so where are we? Here's collaborate, and already your audio seems a bit more muffled than usual. I wonder why. It could be the microphone I'm using. Which microphone am I using? I guess I only have two microphones to choose from, so it's probably from this from the document camera. If I get it closer over here, can you hear me? No.
Can you speak again?
I'm speaking right now.
Yeah, seems a bit more clear now.
Okay, I'll try to be over towards the document camera because I think the Kaltura needs to have its own microphone, which is off my computer. I know this is kind of a crazy mess. Remote stuff, a lot of fun. So let's see here. I got to do that part and share screen with you so you can see what I'm doing. I think it'll let me do 2 share screens. It should, right? Let's see. Boom. Okay, there we are. So we're in the final exam review session here, and boom, there's a lot of topics to talk about. Exam 1, we covered all this stuff. Exam 2, we what was, there wasn't on all of those problems weren't on the exam, but after exam 2, we've had welding and spring stuff. We didn't go into too many additional failure modes upon except for yielding for springs. So I was mentioning my fondness for despair.com. You should go and check these out right here. I thought they were kind of funny, relevant in the sense of I don't know how I would say it, relevant in the mechanical design area here. I put them under useful links and resources just a couple of minutes ago, or apparently I didn't. Huh. Maybe they went under notes. Did they go under notes, or maybe they just didn't go anywhere? Maybe I moved them to the wrong spot. So maybe I'm just going to pretend like I didn't say anything. No? There you go. Yeah. So there's the one I have up on my wall in my office. Mistakes. It could be the purpose of your life is to only serve as a warning to others. These are posters you could buy. You could buy shirts or t-shirt. Coffee mugs and stuff with this on there. The journey of 1,000 miles sometimes ends very, very badly. Some of them aren't necessarily relevant. Here you get a consistency. It's only a virtue if you're not a screw up. Right here, so there's a engineering application there. This makes you sad, right? You could, so I shouldn't be cynical, saying that your education is yeah. Anyway, I thought I was going to point these out. I was going to put them into the slides, but I didn't get a chance to. I'm trying to find one. Here's an engineering one. It says it takes a lot less time, and most people won't notice the difference until it's too late. Mediocrity. Yeah. And okay, here's the one I just had. This is what happens when problem solvers get paid by the hour. Right here, so we're problem solvers, so it's relevant. And then unreliabilities. Here's one that's relevant to our mechanical design. Failure is simply an opportunity to begin again. Next time, someplace else where they like to hire losers. Anyway, let's see. Where is I? Final exam. All right, and so. Yeah, I had mentioned this the other day of all these different little charts about people who had came up with designs, how to design things. Design spiral was one that I'd heard early on, and when I was a younger engineer, and they do that actually in naval architecture. There's actually this design spiral where you start out with the main requirements, and you start to go through the various aspects, and then you have to go revisit them and revisit them again and revisit them again until you get to the final design. Um, but like, there's lots of circles and diagrams that people come up with for design. You've had some design experience now, and but these are like actually real things from real papers and real books that describe. Here's the step by step on how you should design things. But this is what I had. So because I missed out on giving you this wonderful slideshow, I decided to include this. And then also, here's something my boss, he had this on his wall. Actually, he had one that was like this: the 6 phases of a project were enthusiasm. Of course, he didn't have it with this great animation, which just makes things better. I like the disillusionment. So, for every design project, you can actually kind of like see where there's like a panic and hysteria, people going all crazy. There's a lot of that going on. And then search for the guilty. Yeah, I always like these little animations, little things. Punishment of the innocent. I always thought that was a sort of sort of a. I don't know if that was actually one that I'd ever experienced, but I did have for like praise and honors for the non-participants. Like people who really didn't have much to do with the actual thing getting done. They usually get praised a lot for it. Anyway. So let's go on to the stuff. The reason why you're here. Oh no. Yeah, I guess so. Okay. So here are some suggested problems. They're up on Blackboard. That are out of the chapter. These are the kind of things. I'm not sure. Yeah. They're probably these might be problems that Dr. Ghosh, when I first came here, he had included, and he said, okay, well, work on these, and then the exam will be based on these. So that was his approach for exam prep. So I went ahead and included those, and the answers for those are listed. Although the problem numbers may have changed, so for depending from edition, the 10th edition to the 11th edition. So be aware of that. I also have posted some exam practice problems. We can go over any of these. I have the solutions already posted. But I came up with something today, and I thought it was okay. So I came up with 2 things. One of them I think was already posted in the exam prep on our Blackboard. Let me see. Let me roll this thing up. I'm gonna find my mouse. Oh boy, that's kind of messy. Okay, under exam prep. So I moved it actually. There was one that was up here, but it was something I had discussed with a previous year. I said, hey, this would be the kind of problem that I would like to do. So I think this was this problem 1 or problem 2? Yeah, this is the one. I think I actually used it as a booster one year for instead of a recoup. I had people and then said, what would happen if I gave you this problem? And then, but I had listed it actually in my files as a final exam idea, just to see if you could, with given a very small amount of information, because the class is called mechanical design something mechanical. And so this is up there on Blackboard if you're interested in thinking about it, but don't waste your time trying to do this. So that was just an idea that I had in the past, and then today I had a bright idea. But we're not going to do it, but I want to use this as a means of review, a means of discussing instead of, in the beginning here. So I'm 11 minutes into this, and I don't want to waste your time. I want to make this beneficial to you. But here's the thing that I had this morning. I said, hey, it would be cool. And I almost said, oh, it would be funny, but it would be kind of at least amusing to me, not to you. If I were to like give you this problem. So here it is right here, is trying to talk through the stuff that we learned in this semester, right? And I start out with and I'm not sure, you guys know who Rube Goldberg was? Have anybody heard of Rube Goldberg? Are you people listening? Are you still there? You can hear me, right?
Yeah, I can hear you.
Do you
Yeah,
know?
the chain reaction machines.
Yeah, the guy, he would make these really crazy, absurdly complicated machines to perform a task. It was sort of satirical, right? It was trying to make fun of the over complex nature of many things in society. Uh, but it was also just kind of funny and humorous. If you ever played the game Mousetrap, uh, it's sort of like a descendant of a Rube Goldberg, right? Everybody ever played
Hmm.
Mousetrap?
I did.
Yeah, it's got a lot of pieces that you have to put together on the thing.
Yeah.
I liked that as a kid. Maybe it's got inspired me to become an engineer. But here you go. We have a mousetrap kind of situation here. Um, as we're looking through this and trying to see, I was trying to imagine all the stuff that we've covered and what kind of machine might use all of this. And I still don't think we have everything in here because we don't have any shoe brakes. But let's take a look at the loading and the cause and effect that's going on here. First, we start off with a handbrake. And I put little question marks in there. If we're going to design the thing, we have to make some of these decisions. There's actually some additional things that we don't have. Actually, the geometry of where that is with respect to these other points is also a thing. But we have the diameter of this and the band width, the coefficient of friction between this band and this. Of course, the overall diameter of the drum and this wrap of the angle, and that actually is closely related to where the center of this is with respect to the pin and the other parts. So, but we going into detail, we will also want to know, well, what kind of cross section will we need of this? And then we have to make a decision as what's going to be an input. I mean, we're going to decide on a force, and well, okay, well, we need to put like a pin in that for a second, but the after we've made all of these decisions, we have this connection between the force and the braking torque, and that's kind of the deliverable that we would expect. Like, how much do we want to torque onto the thing after we've made all these choices? And some of them are just practical about like not breaking the handle, so we want to pick out the dimensions of that, but also the material of the handle. The material of this is going to, and this, well, more the band or the lining inside the band is going to determine this uh, coefficient of friction, and also the maximum possible pressure that you can put inside. You don't necessarily have to use the maximum pressure, but that might be something that we also want to know. We have a shaft that's connected there, and we have a bunch of shafts along the way, but all of them we'd have to make a decision about. Of course, it's material. In this case, is pretty much only going to be torsion so far. I haven't put any bearings in between there. This thing's just floating in space. The rest of them I kind of put bearings in here, but I was getting it. I actually started from over here and worked my way down. So by the time I was getting here, I was like, okay, I made this complicated enough. But we want to know bending's moment and torsion and material so that we could pick out a diameter, right, in our mechanical design process here. And then we got over to belts and pulleys. We incorporated those, so we want to know the geometry for sure, this diameter and that diameter, distance between. That's going to establish what these angles are going to be. We also want to know the bandwidth, and then we have to start getting into the materials. We need to look at the speed, but of course we're only actuating here, so there's no speed involved in this. So mostly we just want to make sure that we have enough preload so that we don't have any slipping going on to be able to transfer the torque here. And I made it big to little, so it may probably make more sense to go from little to big. But that's neither here nor there. We're trying to think about the considerations, the design considerations, and the variables and the purpose of each of these objects as we go through them. Right? We're going to look at the big picture and then dive down into the deep specifics. We got another shaft, and I put a bearing here. I guess it is a set of bearings, maybe, so that this thing can won't have any wobble that way. It can handle the moment. So there's going to be a cantilevered moment right here on this shaft, and then another cantilevered moment on this. Um, and then you got to think about the forces that are involved, right? This one, we're going to make this belt tight, so that overall is being pushed up this right here. But the belt has a different tension between both of these. They both have a preload tension, and they also have a tension because of the torque being transmitted, which is going to be different on each side. Um, Partially because of the stretch, by the way, because these things are going to stretch, deflect ever so slightly. Um, and so there's going to be torsion on the shaft all the way through. And also, like I said, this cantilevered bending here, cantilevered bending here. Some of that's going to be because this actually is going to be a downward. So this one's going to be pulled up, but this gear is going to be pushed downwards because of the radial um, force on here, but it's also going to have a tangential, right? So if this thing is pushing downwards, that means it's going to be pulling on us. And this is all better to do with the free body diagram than what I'm doing right now. But if you want to try to figure out what direction each of the forces are going to go, you really be better off, instead of just winging it, actually drawing a free body diagram of each part to try to figure them out. But then we would get, depending on which way, I haven't actually decided off the top of my head which way this is a thing going. I imagine this is pulling up on here, so it's creating a torque this way, creating it, so that's that torque right here. So it's probably pulling up on this side. So there's a torsion going this way. So it's probably, this one is facing a force going that way, while this is having a reaction force coming this way. So this is also being bent in that way, out of the page or down in that direction, I guess you would say, because of the tangential. So it's got two different modes going on, two different forces that are causing a moment. So you could actually find the plane that force would be in, that total force. Same thing going on here. There's a torque happening onto this, and this is bending this shaft. Only put one bearing on there. Should probably have put two. Doesn't really work very well just to have one bearing. Something as we're entering here now is I made this a pedestal type bearing. That's usually what they call this. And I put a bolted and preloaded joint right there, right? So ignoring the, well, we could look onto this that they're, no, I'll take that back. Anyway, this joint is going to have an upward force of it because of the radial of this, right? So that this will have a certain amount of upwards force taking place on it. It's also going to have it's also going to have a radial force coming this way. So this is my preloaded joint right here. I was really stretching to try to find a preloaded joint and to have what the preload stretch of this would be for some type of criteria, right? But in a design, we'd have to pick what the diameter is, pick what the thicknesses are going to be, pick what the materials are, what grade of bolt we were going to have, and then of course what the preload's going to be. But then we would have to have some criteria of what we wanted to base this on, or several criteria. It could be that's the safety factor with respect to proof load of the bolt, right? That was NP. It could be the opening, like we don't want to open, so it was the separation one. One that we probably wouldn't use is the NL, which was like the load factor. That's just a convenient, it's not even really a safety factor nearly as much as it is a parameter to see how the bolt is being used. So we could talk some more about that. On here, I have a drum and a cable, which we covered. I also have a bolt pattern right here. That's going to be, some of this is going to be a vertical load that's going to be placed onto this. But it's also, yeah, because it's going to have like a moment, because this is off-center from that. So it has to withstand this bolt pattern right here. So there's a primary and secondary shear taking place on here. And then I came here and I have a spring attached to this cable, and we're going to have to decide, well, how much are we going to allow this thing to deflect, because that's actually inevitably going to come back to how much this is going to move right in there. Um, and so we kind of have to decide what these forces are, right? These interrelation of all these forces that are taking place, and then get the specifics of the spring, which are importantly the mean diameter, but probably want to tell, the answer is the outside diameter when you're trying to design the thing, and the wire diameter. So those are the two main diameters, and from the materials and we can get what the spring is going to be, the K, and get what the loads are. And then we have, lastly here, some welding design to do. And so this is going to be a welding pattern. And I have it from the welding symbols here. It's like a C shape. So we would use that to find, and maybe the goal here is to get the H, right, to get the leg height. So anyway, I wanted to think through those ideas and the mechanical design for all these as a means of review of the kinds of things that we would want to investigate. But now I know what you're really here for is to do problems that are similar to the ones that are going to be on the exam. So I'll take questions of types of problems that you would like to look at, and we could make them up, or we could pick them out of the book, or look at previous homework problems, or example problems, or whatever.
I think it might be good to go over some ME370 stuff that we haven't done in a little while.
Okay.
Yeah, I agree.
All right. So I had okay. So is there any specific thing that you were thinking about?
Nothing in particular, just more so what would be like the important things that we might consider. Obviously, moments and alternating stress and that type of stuff.
Okay, so one of the most important aspects to me is that students can take a relatively basic problem and work it all the way through. And so a not necessarily a joke, but a jesting truth that I would talk about in ME370 type problems. We really only kind of had two types of problems. We had door handles and 3D shafts. So the door handle and let's put some kind of 3D shaft looking thing right here. So we've done a little bit of that with some of the shaft things. I tried to keep it. I think it's several assignments or things where we had to take a look at design, and then we do have fatigue design, but we also have static design. So things are either static, so we're either looking for static or dynamic. But I don't like saying dynamic because that makes it sound like we're doing accelerations onto the thing. We're really just do static and fatigue maybe onto those. But each of those, what you start with, you have to be able to do an FBD to get reactions. Almost always it's going to be axial, bending, and torsion. We could also include on that list to have transverse shear, but a lot of times that's a small value that doesn't happen at the same place as where the maximum stresses are going to be from these other guys, or especially for bending. So because of that, we can usually ignore it. It's very very common to ignore transverse shear in those situations. You can't in some circumstances, like on a ship when you're doing the hull, the transverse shear is one of the, is a pretty large amount because it's everywhere along the length of the ship. The cargo and the ocean are pushing up against each other, causing a shearing action. So that's something you actually have to be pretty cognizant of. But for like little door handles and 3D shafts, they don't usually count. So, taking a look at a door handle problem, which is something that I have considered asking. Like, for instance, I have asked it before, in something along the lines of like, oh, I don't know. I'm not giving anything away, by the way. I'm just going to say I might go something along these lines right there. And I don't know, put a load right here and right here, and ask you to give me the safety factor against failure, yield failure here at the base, right? So you'd have to have a bunch of dimensions to be able to do that, right? So I have to be careful with my drawing a little bit. I could just randomly pick out some things and see what happens with the numbers. So like I'll say that this is, I don't know, let's make it 8 inches and make this thing 9 inches and make this dimension right here 6, right? These are my random numbers onto the thing. And I will make the diameter of this, or I could solve for the diameter of this as being a design problem, right? And I could base it on if it's going to be static, right? Let's assume these are static loads. We could say design. So I don't know if I can do the design one off the top of my head. Tell you the truth, I might have to cheat off of that because a lot of times you have to do a little bit of algebra. I could probably look it up in Shigley and modify a question. But let's, instead of a design, let's just do an analysis, right, of a 370 problem. So analysis. And say we want to find the safety factor against yield, and I'll say von Mises. It should be a von, not a vom. And so the diameter here, let's try to get it like something proportional to it. Let's call it 1.5 inches in diameter. And then, what do you think for loads? So see, if something this big, trying to picture what it looks like. This is almost like, yeah, well, it's almost this. This is a distance for the 6 inches for the thing. So like, could it take 100 pounds? Let's make it 100 pounds here. Let's take it 150 pounds. I don't know. I'll try not to make this one too long, but I just want to talk. I'm giving you an example of something I would expect you to be able to do, right? After having taken ME470 and taken this course. And if I was going to have a junior engineer and I was going to just say, like, how much of the stuff that they retain from, for basic things, this is what I would ask. But that, that might be mean of me, but I would still do it. So I would start out with the FBDs, right? The FBDs of this. And you can do this with vectors and that kind of thing, but I think it's much better. It's my preference to always use two-dimensional things to break the thing down into 3 views. So not everybody's comfortable with that. I made my ME470. People always do this, where we take a look at the 3 dimensions that we would have, and I drew it in kind of such a way that it'll force you to actually think a little bit, because I drew it coming from this side, from over here, looking at it from that direction, whereas it probably would be much easier to view this. So it's a little bit of a challenge, but I kind of doing it because I want it to be a challenge. I want you to be able to test whether you can visualize how something is laid out right here. And so in the X and Y view, which is coming from this direction right here. This is where it connects to the wall. Remember, do not draw the wall. The wall does not exist in a free body diagram. It has been cut. We have cut right here at the wall. And so do not draw that. No, wrong. I mean, you may not get the right numbers, but you're conceptually breaking the thing down, because we're looking for stress, and stress is inside the piece. You can't find stress if the wall's still there. So it seems like I'm being nitpicky, but it is the concept of the thing. All right, so we don't have anything going on in the vertical direction, but we do have something in the X direction right there. This is in the, I just labeled that Y over here. That should have been a Z, sorry. So I'm going X, Y, Z, which is my preferred way to do it. And it's a right-hand rule where this X is your thumb, index is Y, and this is Z right here. So we got the right-hand coordinate system, so we're golden. We're going 150 pounds. This right here is going to be 6 inches. This right there is going to be 8 inches according to my numbers. And then so, okay, so we're going to have the only reaction force is going to be in the X direction, because there's nothing in the Y, and we can't see this one because it's in the Z. So this is going to be R, and I'll just call it RX, because I didn't label what these letters are, so I'll just call it RX. In terms of this moment, we can figure it out, but it's not going to be one of those problems where we can't figure out the moments. But one of the views, and it's actually one of the things I'm testing here in terms of statics, is can you get the correct reactions? That is like so fundamental and so important in trying to be a mechanical designer or analysis right here, is getting the loads correct and seeing whether they combine and they don't combine, that kind of idea. So this is like, you can make something more complex, and obviously I can make it simple, but I think this is about the level of complexity I think you should be able to achieve in a short amount of time. And so this one is going counterclockwise if you were doing a point against here. So therefore, this one must be going clockwise. Did I say that right? Yes, I did. And so I put an M there, and I'm going to say it's an MR to make sure you know that it's a reaction moment, and I'm going to put a Z because it's about the Z axis. So I don't necessarily have to go the sum of the forces in the X direction equals 0, because this one is so obvious that it's negative Rx plus 150, and that we know that Rx is equal to 150. So I'll skip doing that with the other two views, but it is true that you would want to do that if there were a bunch of different forces in all these different directions to keep track of stuff. So this guy, and this is one of the things, oh man, this is a huge pet peeve of mine. I can't stand, I'm going to call, we only have one spot we're doing it about. So we can just say that we're taking the sum of the moments about the Z, and then people start writing stuff. And I just want to strangle whoever it was that told you to do that. Because this is, I find it to be instances where this could be dangerous, that you would get the wrong signs at it. It does not equal something else. It equals 0. That is true. And what people will often do is they'll think that is the reaction. That is not the reaction right here. This little letter right here is all of the moments. The reaction is one of the moments. It is not this, it does not. So what people will do is they'll mistakenly think that this is that, and then they'll start writing these other guys, and they'll be done. And you will have gotten the wrong direction. And the wrong direction can kill. So do not do that. Crazy thing, shortcut, that for whatever reason gets taught somewhere, and then it's getting repeated here by professors that should know better, but do not. So looking at this, we'll see. We after having written this, we write, oh, it's negative MRZ because it's a reaction. Then go, okay, what other moments are on here? Well, we're taking about there, so that doesn't cause any. This causes a moment, and it's a positive moment, and it's 150 times 6. And I think students don't believe what I just said. They think I'm full of crap, and I don't know what I'm talking about because they could have just looked at that and said, okay, that reaction force is 150 times 6. Why would I bother ever writing it out the other way? Because I made a simple problem for you so that you wouldn't you wouldn't take it forever. But the real world has complex problems, and if you're going to shortcut here, you'll shortcut there. I know it's a rant, but it's important to me that students learn the proper way, and I'm almost offended by the professors that don't teach the thing correctly and are lazy and promote laziness. All right, so my next view, I'm going to choose to go in the YZ direction. So here I'm looking in that direction right here. So there's Y and there's Z. And now from that view, we're going to see this horizontal and that vertical. So we're going to see it coming out that way and down that way. And here is kind of like hidden from us is the end point that's right there. And that's where that's really the thing that's been cut is kind of behind this. So just consider that. And now we're going to see the 100, but we're not going to see the 150 because it's coming at us in the X direction out of the page. So we got 100 pounds. By the way, I think I just enunciated better than I ever have before why you should be doing it the way that I've been trying to teach it. So I got to remember to keep that spiel the same. All right, so now we take a look at the reactions that are going to be here. Okay, well, it's a simple reaction right there. We'll call that RZ that's happening at that point. And we can skip in this instance to know that RZ is going to be equal to 100. That's totally fine. And then there's nothing else there's nothing in the Y direction right here. And now we have to take a look at the moment and figure out what direction it's going to be. This looks like counterclockwise again, so this is clockwise. So we know we could actually write down that RZ is equal to 100 pounds. And not so exciting, not something to worry about. So right here, we want to do the sum of the moments about X. And this is going to be a particular moment. So I'm going to give it a name. He's torque, right? Because he's twisting the shaft. So I don't have to go the MR thing because I just want to, I'm doing the MR thing because I want to make a distinction between all of the moments and a particular moment, which is a reaction moment. So right here, this is a particular moment, which is a reaction moment that's a torsion. It's a torque, right? So I'll write that negative T down there because he's going clockwise, and then I'll have a plus 100, and I think it's going to be 6 again. That's kind of boring. All right. Equals 0, so I know my torque is going to be 600. I can do that math. All right, so the last one might require a little bit. Now, I think I can squeeze it in here. I'm not saying that's the right thing to do, but I can squeeze it in. I've had a lot of students this semester, or quite a few, that have been making it very difficult to grade the thing because they'll go all over the place. Sometimes they'll start to go down the page and then back up the page and kind of curling around, and I can't find anything in there. So I'm probably not being a good role model to what I would like to see. But what's left is we're going to be looking down on the thing, I think. Let me see. We did the YZ, we did the XY. I think we need the XZ now. And so I kind of have to draw it from the side. I'm looking at it from above. I think what I'm going to see here. All right, I've messed with myself here. Let me go X that way and Z this way. Right, so looking back up here, what I've done is I've kind of rotated it here and I'm looking. I don't have a good spot to put my big eye. Maybe it's like this way right there. If you can, if that makes sense, right? I'm looking down and it's going up, right? So anytime if you're having trouble with the visualization, you could just go with positive and negative. You can see that here's the, start from right here. We can say, oh, we're going positive, we're going positive. Oh, now we're going negative Z, right? So if you're looking at this thing, we could go, we're going over this way and then coming back down. And here is where these forces that I chose in here become particular and important to note, right? So one of them is going to be in the this one right here is in the positive x direction. That's this 150 right here. And then here is in the negative z direction. So there's the 100. And then the dimensions that we care about, this is going to be the 9 inches, and then here is going to be the 8 inches that we cared about to the center. So reactions, we're going to draw the reactions on here. We have this Rx, which we already figured out, and we're going to have an Rz, which we already figured out. Here's the big important one. We're going to have this moment right here. And that moment, notice this guy's going clockwise. This is going counterclockwise. So we don't know what I'm going to call MRY. That's the reaction moment about the y-axis, moving about this axis right there. And because this one's clockwise and this is counterclockwise, and this is a different value from that value right here. We could probably predict it, but it's better to just choose the positive direction and see what happens. So I'm going to write it over to the side. Well, I don't like that. I want to move it underneath it. So there's going to be some squeezing going on. So we got MRY, which is a particular moment. It's not that moment. This is just declaration of all the moments. This is a particular moment. And then we'll go with the positive one first. 100 times 8, because the 8 is the distance that's, that's perpendicular to the load right there. And then minus 150 times 9. And you can almost tell, well, this is the larger load and the larger distance, so it's going to negate that. You're also going to see that this is negative, so it's going to drop over to the other side, the equal. So we actually did choose the correct direction by picking positive. But it's going to be a smaller value because these two partially reduce each other. All right, so you can just speak out. I don't mind being interrupted. It's harder to actually to respond to the I can't remember the words to the chat things, but I can just put them up there if you want me to. So it's 550 inch-pounds. Right. So that right there was just statics. And you're like, well, that was like 3 courses ago. Like, why the hell? Why would I be picking on these things? Because it's the be all end all. I mean, we took statics for a really important reason. You have to start somewhere, and if you want to try to be a designer or something, you got to know the loads. About the grading of the final, will it be based more on correctness or work shown? And, well, it's really kind of more heavily on work shown than correctness, because everybody makes mistakes. But if it's conceptual mistakes, then that definitely counts. If you skip things that should have been done, those are bigger points. If you don't do it at all, those are huge points. So those are the taxonomy. Is this going to be graded like the first exam? It's going to be graded as fast as I possibly can. So there's going to be a lot of times what I'll do is I'll go through there and I'll put a bunch of X's on it, and because I have the pages in front of me, yes, I'm going to look through there. I'm going to put a bunch of X's on the same problem for everybody, and see how everybody did, and then I'm going to estimate the percentage successful. But you probably won't see it because it's not scanned or anything. So I have no plans to upload it, but you can come visit me afterwards and to look at your individual exams. I don't mind that. So we want to summarize and start to get to now the stress is part of the thing. So as you do the statics part, and so I'm going to get the total bending moment because I have it in two planes. I have it about the y-axis and I have it about the z-axis. So there's going to be a total bending moment that's going on in this, just like we did with the shaft, and we had two separate planes. We have two bending planes that are taking place. I have a 3D printed little door handle thing that's much easier to explain that with, but I don't have it with me. I should print out some more now that I have my printer working. It's a great little tool to do things. So anyway, here's the max moment that's going to be taking place. It's going to be the MRY squared plus MRZ squared, or the square root of 550 squared plus 900 squared. I did that right. And did I do that right? Yes. And so we go 550 feels like I made a mistake already, but it's okay.
Don't we also need MX as well?
Yes, but we got that with the torque. So the torque is about the X.
We're only doing. So is there a reason why it's not included then with the other two? Besides it being T?
Yeah, because it's a different stressor. It's a different type of stress that's it's going to cause. It's going to cause torsional shear. This is going to cause bending. So we could do. So we're all set up right here. We with our loads, and we can go to stresses. And the first thing we can go axial. Axial stress is going to be. I guess I'll give it. I wish I had like better or decided on some subscripts for these, but we're going to have F over A. And coming back to our reactions, that Rx is really going to be the guy that's causing axial, or you can think of it as being 150. Either way that you want to think about it, it depends where you're considering where your stress element is going to be. And maybe I should point out to you. I think it was Nick. Yeah. Another approach that I use in ME470 is instead of using the FBD, you could also use what I call the stump, right? So like we're pretending this thing, maybe it was connected right here and it went on a little bit longer right here. So we actually cut it before we got to the wall. Let's pretend that. And so if I was going to ask a problem in the early part of ME470, I usually will have like little stress element specific stress element locations on there and say, okay, for that element, tell me the stresses at that element. But then as we proceed in the course, we go, well, we don't really give a shit about any particular element as much as we care about the maximum one. So the maximum one, so this, we have a bending that's going to be taking place specific to that spot. And it might be tension here if I did it correctly. I think I did. No, actually, I think it's going to be compression here and tension here. And then, because I'm looking at this guy right there. That right there, notice it causes compression at the top, the way it's drawn. And it causes tension at the bottom because it's kind of pulling on the piece. you can think of it in the opposite thing happens when you're in this right here. Is it actually has see if I'm drawing it this way. So this is this is clockwise, but looking in this way right here, this is actually counterclockwise, which would be looking like that right there. So that's still compression here at the top. And then we want to look over at this guy. We're looking at the top view, and we end up going clockwise, no, counterclockwise on here, which is that way. So it must be clockwise on here. So we actually have compression there and tension here. So we have tension here and tension here. So generally speaking, it's going to be somewhere in this zone for the tension that we're going to use that we created from this moment. So if we were trying to get into specifics, that's how I would approach it. But we just know that this thing is going to be a value, both tension, causing both tension and compression somewhere. And since we can look at this one and say it's causing tension, we would combine them to get the worst case. So we got tension and tension together that would cause the worst case onto this. And I probably could get the section properties of this and proceed with that, or I could just do that inside one equation. So there's 150 pounds and pi over 4, and it was 1.5 inches squared. So it's probably going to be a pretty small number, 1.5. I usually start with the diameter, it's just a habit. I think I did that correctly. So if we wanted to know, that would be 1.76. So that's really going to be a small number here. So I didn't set up my problem all that well. That doesn't look like it's possible. 1.5 squared pi times 4 divided. Yeah. And I should divide 1,050. Well, I actually want like 55 by that. Yeah, so we have 596.9 psi. Not a lot. There we go, bending. And because it's circular, we can play a little game if we want to. So we can either go MC over I, or we can go, I hate doing this. I think it's 32m over pi d cubed. Does anybody want to tell me that I got that correct? Somebody tell me if I got that correct or not.
Oh, like the inertia thing?
Yeah, because what you could do for I is, you know that I is pi over 64 d fourthed. And you also know that C is equal to D over 2. So the 64 and the 2 turn into 32. And that D cancels out one of these D's. So you have pi D cubed underneath there for I. It's just a shortcut you could do for circles. I think I got it right. I prefer to do this most of the time, but I recognize that it's a legitimate shortcut. I think I just screwed this up. Yeah. I'm sorry.
Yeah, that should be 84.88 psi.
Yeah, thank you. Sorry. Yeah. Say that again. 80 what? 84?
84.88.
I have no problem about texting if that's the case, Justin. It's all right. I just sometimes, depending on how I have my my dual monitor set up, sometimes it's just that I have to like move things around when people. But I have it set up right now so I could just leave it. I could see what you text. It's not a big deal. So anyway, this one right here is going to be pi and 1.5. And like I said, I just was randomly choosing numbers on here. So this one might be dwarfed by this one, or I don't know. Maybe we'll see what happens. And this really, I think this should have been a 50. No, it doesn't matter. I'll stick with 54. It doesn't matter. Boom. And pi divided and 1.53, and I just lost my place. Where was I right here? Boom. I think I get 3,181 psi. I think I do. My brain's drifting around. All right. So here's this, and because this is going to be, I should mark, this is tension, and this is actually tension or compression, depending on which side of the thing that you're looking at. Like I said, here's the tension probably position if I thought it through the right way, and here would be the compression, and the tension will add with the tension. Tension and tension add together. So here is the total. And this is in the X direction, by the way, if you're thinking of it, because that's, we're looking at a cross section right here. So it's in the X direction that way. Boom. And so they add together, although it's, Jesus, 3,181. I'm looking at my time, and I already spent way too much time on this part of it, but that's okay. I'm going to get it done, and then we can do to the next step. So we say 84.88 and 3,266 psi. The next, we want to go to torsion. And we're going to have tau is equal to TR over J. But similarly to what we did up here, you could always skip a little bit and go 16 times T pi d cubed, because it's a circle. And we have a lot of circles. So 16 times, and the torsion is the 600. And for that, it ends up, just from geometry, a lot of times that ends up being pretty typical, where the torsion is less than the moment. And I have figured out ways to make it where it's in the same ballpark, but also because J is twice what I is, because remember that J is pi over 32 d fourthed. The shear stress generally is going to be a smaller value for these door handle things, and this happens a lot. Not saying it's a rule. What did I do? Okay, 3 raised divided, and so it says 905.4 psi. So not a whole lot. We could do transverse, but because we're looking at the maximum location of stress, it becomes sort of a hassle, because there's actually two shearing loads, or two transverse shearing loads. Is that true? No, there's only one. Yeah, so there's only one. It's this guy right here. The RZ is the transverse shearing load, and it's going in this direction, but only part of it will have an influence on there. If you remember that transverse shear, has sort of the opposite effect of what bending does, right? So if you had this load right here, and then we'll say that this is the transverse shear going in the Z direction, and then you had a moment that was caused by it, the transverse shear is going to be the worst right here at the top and the bottom. Opposite, like the transverse shear is going to be 0 right here and 0 right here for this loading right there, which is, yes, some of it would be like right in there, which is the spot for us, but not only a portion of it. It's not very large, so we're going to neglect. Excuse me, that was gross. So we only have the total. So I'm going to go to von Mises, and the shortcut for von Mises is going to be square root of the normal stress squared plus the 3 times tau squared. Now in the book, that equation actually doesn't really ever show up anywhere, which is kind of a little weird. I don't know why they never put it in there. But if you were looking for it like, hey, where do I find that in the book? Which is a totally legitimate question right there. Um, First, you could go to where'd you go? Where'd you go? Where'd you go? This equation right here. Let's see. Let's zoom in on it. So that equation right there is basically what we're dealing for. We have plane stress, but we have no stress. Okay, well, okay. So this is doing x and y. What we for ours we would just do. We would be looking at it in the. I'm sorry. Let me thinking about the cube.
XZ plane?
Yeah, but we're actually kind of being in the we're out of plane. Actually, definitely X would be one of them, but we have to create a new plane because we're doing the maximum thing. So we're kind of getting a diagonal plane that's somewhere located between the XY plane and the XZ plane. It's kind of a diagonal plane. But anyway, that's the idea. But we only have a stress in the X direction. We don't have it in the other plane direction. We would if it was a pressure vessel. That's like the only instance where I can think of where we would actually need to use this equation. So most of the time, this part of the equation right here, whoops, right there, that's usually 0 right there for most stress situations. So losing my, there he is. So this is that equation. It's just we've gotten rid of the other one in there, and so we can go 3,266 squared plus 3 times 905.4 squared, and we end up with that's a common so there you go. Square that multiplied by 3, flip that over, square it, add it, square root it, and we got 3,623 psi. And if we want to find the safety factor for yielding, we have to know what the yield strength is, and I'm going to go with A36 steel because it's the easiest one to do, and that's going to be yield strength of 36,000 and divided by 3,623, and so the 36,000, and we're going to have a safety factor of 9.93. 9.94. It's fine to round up. I don't care, but I don't want more than 2 decimal places in a safety factor. I think that's a good communication to say I don't know this. I don't. There's all kinds of uncertainties when finding loads, especially. But we've already talked about the uncertainties, and that's what the safety factor is kind of like trying to say. Well, okay, how much margin when we're finding the safety factor, we're usually doing analysis, and that says how much margin do we have remaining, and we can compare it to required safety factors. So I know that was a long problem, but I talked a lot during the thing. I don't think it's so long that you couldn't do it easily. A student couldn't easily do it in a half hour. So you'd want to be able to do this. And by the way, this type of problem, if you wanted to see the source of it, or I'm just doing a variation on it, is located in like they have these guys. So we have this guy and this guy. This is in the 10th edition. In the 11th edition, I think they've added in another door handle problem. But these are what I call the door handle problems. Other books have them in here, but it's a very, very common type of problem. And it's just a cantilevered problem, right? So that's the idea. Like you could even think of that as being a door handle problem. It's just a very simple door handle problem. You think of this as a door handle problem. It's just being a cantilevered problem as opposed to being a simply supported problem. But these are the core of being a designer is to be able to be an analyzer first and to be able to organize the geometry and the loads to get the stresses. And then to be a designer, you need to go backwards and find. So what we could do instead is do a little bit of algebra to be the designer, but pretend like you don't know to find D for a design factor equal to 2, right? So what you'd want to do is work backwards, and you go, here's my allowable is going to be my yield divided by my design factor. I haven't decided yet. I was just in the midst of writing it. What I really want to ask is this one, Justin. See, this is me being mean right here. This is what I really want to ask. I want to go like, no, I'm not going to ask the problem. You weren't here for the earlier part of the thing. I was just trying to use that as an example of what I want to do, but I can't do it. So I'm just gonna, yeah. I'm not that cruel of a person. I hope people. I don't know. Maybe I seem that way. Yeah, I'm almost crap. Don't do that then. Okay, cool. So like if you're gonna go ahead here and yeah, I agree, Nick. No, I thought you were doing the throw up icon. Okay, I was gonna do the throw up icon. So 30. Let's do the safety factor at 36. Design factor. See, that's the difference. Is we found a safety factor. Now we have a design factor, and we said here's the allowable is going to be 18,000 psi, right? And remember that's normal stress, so we need to use von Mises to turn this into normal stress. So von Mises is the square root of this, but which we found to be, oh, but this makes it difficult right here. Here's where some difficulty lie. We have to go. Well, we can simplify a design problem for ourselves and say, well, axial stress was so little compared to bending that we could make ourselves make it just a little bit easier for ourselves to ignore the axial. We could. So let's just write that. Neglect axial. And what we would do is we would include that in the end saying, a disclaimer that we neglected it. But we could put it to here and we wrote, let's see where we had, I'm losing my mind. Okay, right here. 32 m and then pi d cubed plus 3, and that's going to be squared, 3 times 16 t pi d cubed squared, right? And then we say we're going to set that to tau allow. So we can go 18,000 equals the square root of 30. And I guess we could do some algebra first, I guess. I don't like doing it. I just don't like it. Just don't like it. But the truth is, we could actually, if we wanted to, instead of doing the rest of that, we could greatly simplify our time by coming to chapter 7, because they already kind of did it for us. Yeah, chapter 7. They already kind of did that algebra for us right here. Because if you think about it, all right, so this is the 10th edition, which is different from the 11th edition slightly. But right here, they did all of that algebra for you. You could just ignore everything that is MA and TA because it's not a fatigue problem. There's not an alternating moment. There's not an alternating torque. There's just a constant moment and a constant torque. And we're not using ultimate. We are using yield strength. And right here, we already did the N and this right here. So I could write all of this out. If I could remember it, here I'll grab it and put it onto my other screen. so I don't have to keep flipping back and forth. Where'd you go, buddy? There you are. Get over here. And there you go. So, doing the same, this right here, what that will result in, if you do the algebra out from this, you will have, I guess I'll write it like they did. It was 16 divided by, and I'll like, they also have this built into it, so I'll write that in. And pi, and then 1 over, and instead of ultimate yield right here, and then 4 times, and then we can leave off the stress concentrations, right? Remember that they're putting stress concentrations into there. We're going to pretend we're looking at a place where it magically doesn't have any stress concentration, so we can ignore these guys right there. So that equation simply becomes, let me see, I just lost my place. Yeah, I don't need this parentheses, so I could get rid of it. M cubed doesn't have to be M because it's not cubed. What the hell's wrong with me? Squared, right there, plus 3 times t squared, and then this is to the 1/2, and that's a closed brace, and to the 1/3, right there. So that right there is for a static case right there. And I don't know why they never write this out anywhere in Shigley, but you could make the case that they don't need to because it's right here. Right, it is written right here. And I know that in the 11th edition, they decide to put an A and a B, a capital A and a capital B, in this same spot, but it serves the same purpose. So just be aware if you were to design something and you need to have this type of situation, it's fairly straightforward after you look at it. So we could get what the thing has to be, right? So I went ahead and we knew this was the allowable. We'll use the 36 right there. So the 16, the design factor, maybe we should put a D right in there, is 2. Pi right here, we're going to have 1 over 36,000. And then 4 times the moment that we had up above, which is, where'd you go, man? Where did you go, moment? 1,054 squared plus 3 times the torque, which was 600 squared. And then the whole thing square rooted, and then the whole thing cube rooted. And if you get something stupid as an answer, you screwed up the math. I can't stop to tell you that when someone writes that down as an answer and doesn't at least acknowledge that they screwed it up, it makes me nervous. I mean, it might very well be that you knew what you were doing and you knew that it was messed up and you just were running out of time, so you had to move on to something else. But I would suggest it would be a smart thing to just write, like, just a quick note. Yeah, that's not right. Something's wrong here. As a professor, I look at the thing and I go, I'm a little concerned that you just thought that was totally okay to write that down, when it can't possibly be 0.05 inches. It's just not, no, it can't be. So, all right, so I think I got that right. I'm going to multiply it by 16. This is a little concerning, the values. Multiply it by 2, divide it by pi, and then I'm going to take the cube root. I'm still a little nervous here. All right, so I'm going to take, that's a 3, and I'm going to write to there. No, that can't be right. No, I must have messed something up somewhere along the way. I don't know where it is. Because I was talking the whole time. 600 squared. Gonna have to move on, right? Times 3. 1054 squared times 4. Add them together. Take the square root. See, did I do anything wrong? Let me double check my thing here. Don't trust me. Square. Okay, square root. Then divide by 36,000. All right, that's actually looking better. I think I forgot to take the square root. I think that's what it is. Yeah. 16 times 2 times, and then pi divide. And now I take the cube root, inverse of that, raise it to that. Gotcha. That makes sense. 0.8728 inches is what's going to be the size, right? So if you were doing a design problem, that would be the approach right there. But you wouldn't give that as an answer. You would probably look it up in the preferred sizes. Because remember, we're in a design class, so that's what we're focused on, right? Is designing things. And you wouldn't answer a design with some crazy number. I didn't mean to say ass. Some crazy number. We look up in table A17, and probably the one I like is 7/8, probably, right? 7/8. I'm a traditionalist. I like fractions of inches. They have decimal inches. They don't have 0.9 for some reason. So 0.8 wouldn't be large enough from our because we have 0.8728. But 0.875 is a nice little number right there, right? So that's what I would pick right there. I think 0.9 is fair. I'm not a stickler for having to be exactly along these lines right here, but I think sometimes anything weird is a weird number right here. So I'm going to go 7/8 of an inch diameter would be the answer. And for von Mises equations, are we allowed to put in a sticky note in our book? That's not in a book. I really don't want to start going down this road about negotiations, and so I just stick with what's in the book, man. You can remember it. I believe in you. Okay, so that was a really long one, I know, but I recognize that not everybody had me for ME370. So this is a fundamental equation. I could also turn this equation or this type of problem into one that's more relevant for what we're doing, which is the welding problem. Like, what would happen if you had to weld onto this thing? And we're dealing with this right here, that kind of thing. So we want to, first off, the welding symbol that you would have is probably that guy right there, and you would say to weld all the way around. And you would not draw it this way right here. You would not draw that one because you don't want to have to weld on the inside of a pipe, right? That's what that would mean, would be on every side of this thing. But our difficulty in doing a welding problem on this is to figure out how to distribute these loads. Not too much differently from what we have here. I might simplify it to some extent. Maybe not. No, I think. No, I would probably go along these lines. We do have. Boy, it's a bit of a tough problem. I'm trying to remember how I addressed this in the past. The fact that we have two different planes. We would go to the welding here, and we would go to the two different modes, and you were combining the things together. So we have a bending thing taking place. Oh, by the way, I guess I mistakenly said just a second ago that we could put a thing in here. Well, this is not a pipe, right? It's not a pipe right now. So the only way that you could put it is to put a fillet right there, because there is no other side to do the thing. If it was a pipe, there would be another side into there. Uh, so what we would do is we have two things. We have the torsional one, the torsional case, where we would have. Okay, first off, I'll write this down on my page. I know you can't see it, me writing it down, but I'm going to write down 1.414 pi HR, and then I'll write JU is equal to 2 pi R cubed. And then we would also go to the bending case, and we'll see that that's going to be case 9. They have the same A, slightly, actually not all that much. Yeah, just slightly different. The IU is going to be pi R cubed. And like we often find with these things, the J is twice the I, right? Just like as in regular old bending taking place. I want to remember that we want to turn this IU and that JU back into a solid J without a U. That's the U is like per unit, I think. So we want to make sure that we write down this equation right there, as a reminder to ourselves that we need to have a J is going to be equal to 0.707 HJU. Just write it up. IU. You see, and now I can remember that from 2 seconds away from each other. HJU, and that let's see, like right there, boom. I wrote it in 2 separate. I keep messing things up. I'm getting tired. 0.707 H I U. All right, so for this loading condition, maybe we're going to go ahead and if we're going to follow the rules as they say, what you should do when we find the overall stress, we should take the square root of the prime squared plus, and then actually break each of these down. But this is a harder problem because we're on 2 separate planes. So we might want to go ahead and take an approximation of the thing and go bending, and then we can go like torsion to the thing, something along those lines, as a simplification, just because we're not in the same plane. And this is entirely a down. Well, no, that's not true. I'm sorry. This is a more complicated problem because the shear. This is the only shear that would be being created right there. But we also have a tau in this case that is a shear because of the axial, because of the way that they do the treatment. I'm sorry if that's not making a lot of sense. But in the looking at the piece, so I'm taking a cross section of both of the pieces and I'm looking at it from that direction right here. We have this weld, like maybe that's like here we're looking at the top of that weld right there, and we're thinking about a plane that's kind of like right in there. That's why we have the 0.707, because we're crossing in here. So axial is sort of like working against in that place right there, and then that's going to be in a different location than but that yeah, I think we could go ahead and, as a conservative thing, use this right there. Yeah, we could actually add another one in. So if we were going to let's say go work backwards in this problem that we already have. We know that we have the tau bending is going to be, where did you go? The tau in bending is a double prime, and it's going to be, is that, okay, no, this is for a rectangle. Okay, so you got to be careful. That's for a rectangle. So don't use this portion of the equation at all, right? Because we have a circle, not a bending. So that's dangerous in Shigley. You have to be careful not to look at to look at the context of equations. So that's going to be m c over I onto the thing, and then for the torsion, same way, tr over j, or t. Yeah, where'd you go? Where did they put it in there? They did, or they did not put it in there. Where's that equation? Oh, I guess they put it up here. There it is. Okay. So I'm gonna go t. I'm gonna go subscript torque right in there to keep track of it for me. So that's gonna be t r over j. So if you were to try to do this design, which is define what the required h is going to be, you would do m diameter of the thing that we found. Maybe we'll go ahead and stick with our newly designed point 7/8 of an inch diameter with that. So that's going to be that diameter right here over I, which is going to be 0.707 h. That's the thing we really want, times pi r cubed. We can even just make this an r if we want to, make our lives, because that was going to be the same, the radius of the thing. And then t r over 0.707 h times ju, which is going to be 2 times pi r cubed, right? Yeah, we'll be fine. This tau prime here, v over a, I'm just going to go ahead and use only the larger of the two. We had 150 or 100 we can think of as the tau, as the thing coming in here. We could actually, if you want, we're going to go crazy with it, add the others, do it twice. But whatever, I guess I'll just leave it in there. 1.414 pi h r, right? Because that's from this area right there. Okay, so we were almost to the point where we want to start sticking numbers in here, and it might actually be easier to put the numbers in before we go much further into here. Because we're just going to try to isolate these h's. So instead of doing the algebra onto the thing, I'll just write the thing out where we got the moment that we're looking for is that combined moment. Where'd you go, combined moment? Damn you. Okay, 1054. The radius is going to be, I'm going to write it a couple times. So write 7/8 divided by 2. 0.4375. 0.4375 divided by 0.707 h pi 0.4375 cubed. I guess I'll have enough room to stick it in there. You know that we could just get rid of one of these and just make that squared right in there. 1054 divided by 0.707 divided by pi divided by 0.4375 squared divided. So I'm going to have 2,479 divided by h, and then here is just going to be 600.4375 divided by 0.707 h. Then I'm going to have 2 pi. I'll just put a pi in parentheses, 0.4375. I'm not going to be able to fit everything in there cubed. That's going to go away. That's going to go away. That's going to turn into 2. Put down and squeeze it in there. 600.707 divided 2 divided pi divided 0.4375 squared divided. All right, so that's only going to be 705.6, 7.5.7 divided by h. And then this guy, I'm going to go with the larger of the two, 150. I could actually just do the square root of the sum of the squares of them. I guess that kind of will be in the same plane. I don't really like that, but that's okay. 0.4375. This is probably a small number. 150 divided by 1.414 and pi and 0.43. Should be squared, shouldn't it? No, it's not. Oh, I know why. Okay, yeah. All right, so that's just going to be 77.186. Wait, that's fine. H. So, one of the things we need to do is decide on what the allowable is going to be. I'm just going to go ahead and assume tau allow is equal to 0.4, 0.4 yield strength. Because all I know is the yield strength of my 836. But I'm assuming that's going to be a lot more than, or I'm assuming that the welding rod or the welding filler material is going to be a lot stronger than my weld, than the welded material. And the welded material is 836 that we just established. So we note that's going to be 0.4 times the base material. 836 is 36,000. So that's a legitimate thing to do. And so we're going to end up with 0.4 times 36,000. So 14,400 psi. So we set this equal to that. So 14,400 equals the square root of, let's start with this one, 77.18 over h squared plus where'd you go? 705.7 over h squared plus 2,479 over h squared. And we could solve that for h. First thing I'd do, I'd square this. That makes sense, right? Square. Boy, that makes it a large number, huh? So I better fix that pretty soon. And then all those H's are going to come out, right? They're all going to get squared. We could add them. We could use that as the denominator, all of that, and then it's all going to come out to the outside because then we get the square root of it. Yeah, it's going to come to the outside, so we would multiply over that side, and then we would divide over here. So what we would be doing is going the square root of all of these guys. Yeah, I'm sorry. I'm just talking my way through the algebra right here. I'm probably going to screw it up, but we'll see what happens. 77.18. See if it makes any damn sense. 705.7 squared. I'll add that together. And 2479 squared, and add those together. And then, okay, so instead of squaring that, I'll take the square root of this one. Now that'll work. And then divide it by 14,400. And I get 0.1791 inches. And that's a fair value. I think that's in the ballpark of what we would consider using on something that was 1.5 inches. Most of the time, the thing I would go to as a guidance for a leg height would be this right here. It's the material of the thicker part. But this is usually talking about plate being welded. That's how I think of it, as being a plate weld. But we have a 7/8 inch a piece right here. And so if that would be somewhere in between three quarters and 1 1/2. So they're saying to use 5/16. So it's 5/16 is 0.3125, which is considerably larger than what we just found. We found we found somewhere between let me see, what's 3/16? 3/16 is 0.1875. That's about what we found that we were required to do. In a real design situation, you'd probably want to figure out what plate you were welding this door handle to, and see what its thickness is, and you would want to try to not exceed its thickness. If we were just designing it and welding the thing to a plate. So there's some different considerations in here. I think I might default to go 3/16 of an inch, but it would be contingent on what the plate we were welding the thing to right here. So if we're welding this to a plate, so here's the bracket, and we're looking at a cross section to it. We want to look at this thing right here. If this thing is well, let's see. Let's go back to what the 3/16 is right there. 3/16 there. Okay, so 1/2 inch plate is pretty thick. So it also depends on what this is being used for. To be quite honest, like on a ship, I'm giving you more information than you could possibly, way more than you'd need for the exam, obviously. But that's the thought process, right? It's like, what is the diameter of this? Okay, that's 7/8. Well, what's the diameter of this? Or not the diameter, what's the thickness of this? Probably 1/2 inch or less. That would be in there. Well, that would be, this weld would also be contingent on what this would have to be. But this is based on stress onto the thing, so I think I would stick with this value. In the real world, just so you know, we really would want to avoid having to load plate in this manner exclusively. So we would put some type of backing on here, like if it was, depending on what, so we might, on the other side of a plate, if possible, put some type of stiffener in that direction, or even maybe one in the vertical direction. And if it was really important, maybe we'd actually, for this type of thing, maybe even put a gusset plate in there, which is like a little, almost like a little bracket. I'm getting into the details, but in terms of a designer, you'd want to make sure that you distributed the load, and it wouldn't be putting it onto a plate, because you can imagine just locally, messing this plate up. Plates don't like to be uh, torqued, or not torqued, but twisted in that direction. But anyway, let's go to another problem. We got some time left. I overdid. That's what I enjoy doing. I like designing things.
I was wondering if we could do something involving springs.
Okay, cool. We got some off the shelf ones to choose from. We have my wife. Here's one where my wife's. I thought this was a funny problem. I amused myself with this problem. This is Coast Guard Academy, fall of 2013. I'm like, ooh, wouldn't it be neat? Like, you could actually take, if you had a pen with you, take out the spring inside it and try to see what the force that's required to open the pen, right? So, like, if you had a pen, you could just click it, because we're in the open position and the closed position. So you have to define what I mean by open. Go ahead. What?
I get what you mean. It sounds like it would be a good problem to try. Do it.
Yeah. See if it's in the line, the realm. If it's in the range of something that makes sense, like how much force are you actually having to put with your thumb to depress a pen? I mean, it's got to be way less than a pound, right? I would think.
Yeah. Probably
And
half a pound an ounce.
yeah, right here. Well, according to the answers, it's going to be 0.3392 of a pound, right? But
Okay.
I don't think in the solution to this I actually showed you how to do it. I just, and a lot of times that's what I used to do in classes all the time. Instead of giving a solution and a step-by-step solution, I just gave them my Excel spreadsheet that I created and told them what equations to use. And then, like, hey, good luck, I don't know if that's the right way to do it. It might be a better way to do it than what I've been doing. Makes you to be a little more self-reliant. But anyway, let's take a look at the information on this. I guess let me put this onto my other screen, and then you can see me write it down. So this is me, the fall of 2013. This is my first time teaching that class. Actually, so bit of history here. I helped out the previous professor in one semester, and then there's a student who made a D in the class, or maybe made an F in the class. I can't remember. Anyway, he had to retake it, and so they said, okay, we'll give you an opportunity to retake the class. Wasn't being offered, so I taught one student. I had one student. That was a lot of fun. Just having it wasn't. I wouldn't say. I was joking around to say fun, but it was a weird situation. Anyway, all right. So I'm not here. Here's my spring. Blah 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 blah. And one of the first, and the information we had was 0.95. He wasn't a very attentive student, by the way. I was just thought I'd point that out. Oh yeah, the outside diameter is 0.18 inches, and the wire diameter, as measured by me, is 0.0165 inches for a spring. And I counted out the number of total coils was 20, and then the end coils, NE, was what did I say? At each end. Oh, I guess no, I said five end coils. So that's the total number of end coils. So I said there was 2.5 over here and 2.5 over here. That's what I mean. Other information. I assumed that the shear modulus was 12 mega psi. Or you can remember that means 12E6 psi. And I also said that the strength, so the shear yield strength was 0.45 of the ultimate strength. And this was music wire. That was another thing. We had this music wire. And what else? Closed pen. Closed has a del. All right, closed. No, it doesn't. That doesn't mean. That's not just mean the same thing as. Gotta be careful here. That's not the solid height. It just means when you have quote unquote closed the pen is 0.05 inches, and when you open, it's an additional, right, 0.150 inches additional. So you have to tell a story, and this is very much a real life because I'm picking a real life situation. So I have to think of the thing when you put inside the pen, and you've plucked the thing, like it's in the closed position, which is to say that the pen, the tip is not exposed, right? You pre already. So this is the length up here is the uncompressed length. We might want to call this LO right there. The open or whatever uncompressed. All right, don't worry about what the O stands for in this situation right here. But here is the closed, and then when we do the pen right here, we have dot dot dot. Now the thing has, I guess I'll just leave that right there. It has now done an additional amount right here. So that is what I mean by opened right there. So it has the additional amount. Okay, so the force required to open. So we have to define on here. A is the F to open. B is the shear stress at open, and C is okay, and then length for perm def, right? So if you were to take that spring out and just going to pull it apart, first thing to do is to find K. Well, K is equal to come on. Boom, right there. So write that down. D for G over 8 big D cubed N. All right. Yeah. I might not get the same numbers, by the way, as I had previously got. So I don't know. We'll find. We'll figure
Which
it out.
N is that?
This N is the number of active coils. So sometimes I'll put an A into there. That's really going to be the total coils minus the end coils.
Mm-hmm.
So in terms of this one, we had 20 minus 5, so we have 15. We're also going to have this big D. Before we go much further, we're going to make sure we know that D is actually the mean D, which is going to be the outside diameter minus the Y, right? So I should write that as OD. OD minus D. So maybe I'll write, by D, they mean the mean diameter, which is the outside diameter right here. And that ends up being 0.180 minus 0.0165. All right, so it'll be a lot of times it's just going to be a small difference, but because of the cube, it could be fairly substantial. 0.0165 minus. So end up with 0.1635. Yeah, it's not inconsequential. So the diameter of the wire, 0.165 fourth times that G, which is 12E6, 8. And now we take the mean diameter, 0.1635 cubed. And lastly, number of active coils, 15. So hopefully we get something that's in the realm of sanity. All right, I already have this in my calculator, so I can cube that, multiply it by 8, multiply by 15. I'll inverse it, multiply it by 12E6. The dog wants to say hi. She protects us from mailmen. She nearly freaked out earlier today because of the guy that's filling up our oil tank. It just seems weird the oil company decides to fill it up right now, right? It's like, well, they want their money now. So, 1.696. Yeah, but she really freaked out over that guy, over the dude. So it looks like I got the same number I got before for the K. Weepy! Yippee! So the answer to the first part right here, the force to open this thing is, let me think. I got to think about this for a second. Yeah, it's going to be, the force is going to be equal to the K times the total deflection, right? If you were to look on a force versus deflection curve, it's always good to think about that right here. Here's the force it was for that initial deflection, and now here's going to have the force at this additional deflection. This is the force that you're actually going to have to put onto the thing. What you could do is you could start pressing onto this. You'd have to actually have a little bit of force, you know, to get the thing to start moving. So here's a little bit of force that you'd have to place onto the little end thing. Of course, this is not one of those pens. I don't have one of those pens around. Do we even give out pens anymore? I don't know. So anyway, you would end up being 1.696, and it'd be, where'd you go? 0.05 plus 0.15. So you can almost do that in my head, like 0.2, right? 0.2 times it. So 0.339. So 1/3 of a pound. I think that sounds reasonable. Do we have an AbbVie pen sitting over here? I don't know if we give out AbbVie pens anymore. Is that sad? Oh, you know what? Oh man, I think I just remembered. I'm supposed to, see, there used to be one of the drugs she would cover, Tarka, something like that.
So, I have a question.
Yeah, go ahead.
Is that supposed to say that, that delta total is equal to that, or is that supposed to say that, F is equal to that? Oh, okay. It was just covering something up. Okay, I got it now.
All right. I was just looking to see if we had other AbbVie pens. So here's a nice slick AbbVie pen, right? Different one of this. Nice. It's got like a little nubby thing right there on it. Yeah. It's just showing off pens. I don't know. You have a lot of pens. The Teen Challenge, Connecticut Teen Challenge. That's somehow. I think that is. I think it's from AbbVie. We don't have nearly as many pens as we used to. Yeah. Do I seem obsessed with this? I think I could break this, right? So let's see. We want to find the shear stress when this thing is open. So we want to use the equation for this, and we're a Bergstrasser group of people. We believe in Bergstrasser because his name is so much better than the other guy's name, Wall. I mean, I don't want to offend anybody whose last name or is related to somebody named Wall, but that's just not nearly as good of a name. Not even close to the Bergstrasser family. But maybe it's some German thing for me. I don't know. So the Bergstrasser, we'll recall, is this guy right there. So 4c plus 2 divided by 4c minus 3. Remember that c is our all-important spring index. So maybe we want to, I guess we could combine these together. Let's write them over to the side. So c is going to be equal to big D over little d. Big D, if you'll recall, was found up somewhere. Where'd you go? Right there. 0.1635 divided by little d, which is 0.0165. It's probably going to be near 10. I'm going to guess it's near 10. 0.1635. Boom. 0.0165 divided 9.9. 9.909. So our Bergstrasser.
ME is the mean diameter there, correct, for the big D?
I hope so.
Okay.
Yeah, right there. And Bergstrasser. Was ist das? Das ist ein Bergstrasser. I gotta learn German. I think I could learn German. I tried to learn Spanish. Total fail. My daughter told me that we needed to all learn do Duolingo. No, is that am I saying that right? I think so. Anyway,
Yeah, it's called Duolingo, the app.
And her plan was that we would be doing this and for a long time until we could speak fluent enough that one day at dinner when we invited her brother over for dinner because he lives in another apartment now, that we would all just start speaking Spanish in front of him. So it was an elaborate plan just to mess with her brother, which seems very sibling-like. But I failed her, apparently, because although Mrs. Deal is still, oh no, she said she missed a day the other day. She had a 125-day streak going. And of course, just to torment me, Duolingo likes to send me messages that she is succeeding where I have failed. I thought this was important information for you to know. And for it to be recorded. So
For posterity.
plugging and chugging into here, we have little d of 0.0165 cubed. That's a little awkward. I don't like him. So let's see. I'll start with him then. 0.01653. Boom. Multiplying by pi. Boom. And I'm dividing. Yes, I'm dividing. And then I'm multiplying. And then I'm multiplying 6, 3, 5. I went a little cutesy with my calculation here. And I think I got the wrong number. I don't trust my old number. 35,000 PSI? That's a lot.
You're still sharing your screen.
Oh,
No,
I'm sorry. I'm sorry. I keep forgetting this. Sorry. My
No problem.
yeah, I appreciate it. My brain's not functioning correctly right now, or ever. So anyway, I plugged the numbers in there. It was all gone while I was doing this, right? So I was sticking all numbers into there. I don't trust the number I just ended up with. So let me start over. I was gabbing away about Duolingo and shit like that and stuff, I guess. 392. It's really easy to make mistakes. Make them all the time. 0.1635. 1.136.
What did you get for the torsion there?
Not quite torsion, but it's kind of torsion. I'm trying right now. I didn't like the number I got, so I'm trying again. But now,
Okay.
now I've just forgotten what I was doing. That's okay. So divide. This guy's the culprit, I think. 0.0165, 3, and now divide. Yeah, okay, I got the same thing. It's a large number. 35,700. That's going inside. That is taking place inside here. That is crazy. That's a lot. But we're going to go, okay, so that is what we're saying for part B, the shear stress. But let's see, actually, first off, we could figure out what the strength is, right? So we're assuming that it's music wire. And I don't want to cram this all into the next page, so I'll start another page into the thing. So let's find out what the shear yield is going to be. We already said it's going to be 0.45 times the ultimate. And so we can look up, or did I give it to you in the problem? Let's see, did I give it to you in the problem? I did not. So we will look up and find here, let's get the width. Music wire. Let's start saying for you. Music wire. Okay, so that's nice. They don't have to do different ranges for the thing. But here is A is 201. I'll write that down. A equals 201. I don't care what the units are. And then M is equal to 0.145. And the equation for finding ultimate strength is A over D raised to the M. Let me come back to this. There you go. So 0.45. Of course, I keep running out of space. I don't plan that very well. 201. And oh, by the way, this is going to be in kpsi. Just remember that. All right, so 0.0165 raised to the 0.145. And we will go 0.0165, 0.145. We will raise that and take 201 divided, get the inverse, and multiply. Okay, so this is going to say this would be 364. So you remember that's not psi, that's ksi. So you multiply it by 1,000, but then you multiply by 0.45 to get the shear, and so you have 164.0 ksi is the shear yield. Right. So if you want to find what the safety factor is, take the shear yield, divide it by the tau. And so that's going to be, for us, 164 divided by, not 35,000, because this is PSI, turn it into KSI, 35.71. I'll put it underneath it. So 35.71 divided. So we'd have a safety factor of 4.59. We're not even anywhere close to making this thing permanent. We were doing the compression right here for this guy. Now, like, we're going to take this thing out. Can I destroy this pen? I think I can. Destroy my teeth. All right, so now it's like, how much force does it take to like stretch this thing so it won't go anymore? So let's see. What to do with it? Well, let's see. Then we're going to set it equal to 164 points there, right? So we would take all these other things and I'm thinking, just one second. Yeah, so I'd go 164,000 is equal to my 8 times F times 0.1635 divided by my pi and my, oh, I forgot my Bergstrasser. I'm sorry, he belongs right in there. I'll put him over to the side. 1.136. You see, he's not very big right there. He doesn't do much of a correction for the curvature and the shear, but that's what his job is. So I was thinking for a second, or like maybe did they ask us how far we had to pull it? Oh yeah, what length do you have to pull it? So first we want to find out what force you would have to pull it. So we get 164,000 times pi. Look how I said pi. 0.0165, and cube that sucker. And then multiply them, sure. Divide them by 8, okay. 0.1635. Sure, boom. So I need 1.769 pounds to stretch this thing. Yeah, I can see that, right? If we could hang a 1.7, 1.8 pounds off of this, that thing would, okay. Well, let's see what distance we would have to pull it right here. So we would have the del that we'd have to do would be F divided by K. So we'd have 1.769 and divided by K, where'd you go, K? Was, 1.696. So it looks like it's going to be about an inch. 1.696 divided. And we had 1.043 inches is the answer to that problem. But let's check it out. All right, so it's almost twice its length, right? Twice its length. This is about an inch long. Yeah, about an inch long. So how far would we have to pull it? Let's see. So we pull it 2 inches. Let's see. Yeah, it's a little longer than an inch now. Ta-da! Engineering. I think it was a great frickin' problem.
That was a solid demo you did at the end there.
Yeah. We learned, and we can even put the pen back together, and no one will ever be the wiser, except that we got 1,000 more of them. You know what we used to get, and this will be recorded for posterity as well. They used to give us all these plastic cups and plastic plates, and then also a whole bunch of these sticky notes, but they had like, you know, and they all had the advertising the name of the company and the name of the drug or whatever, and maybe some contact information or whatever. But they would give us boxes and boxes, even after the whatever the promotion that was relevant to the thing. Boxes would show up, and my wife was completely convinced that it was just more efficient for them to mail her stuff she couldn't use anymore than it was for them to throw it out, right? So instead of them throwing it out, they mailed it to her so she could throw it out. And more information than you need. At the time we lived, they made us pay for trash, and we just refused to pay for trash. So we actually would go to the dump, or the transfer station, I should say, all the time. And all the guys at the transfer station got really excited when they saw my wife's car or my car, because they wanted all of these cups and plates and pens and notepads. So that was an exciting story that you needed to hear, because they would all like be able to like, oh boy, yeah, free, you know, disposable cups and plates and things. Exciting, I know. All right, so I think we've done enough damage. This was exciting. I hope you enjoyed it as much as I did. And I know you're going to have a great exam. Everybody's going to get everything right. So I don't have to do a lot of grading. I can just make check marks on the thing. That's going to be great. It's going to be awesome. You're ready.
That's right, we are, Professor.
You're ready. You're ready. And you're ready for this problem right here, with this thing right here, that you could do everything along this line. So we got a weld, we got a spring, we got a rope, we got a drum, we got a preloaded joint, we got a joint that's in twisting motion here. We got this kind of weld right here. So this is kind of I think of it as a cantilever thing going on here. We got gears going on. We got bearings. There's a bearing right there. How long is that going to live? We got a belt, and we got a brake. Oh man, it's everything we covered in this semester. We even got a handle on here, so there's ME470 stuff. We could even say that this guy right here, we could even like, what is the diameter of that? This is like a door handle problem because he's kind of cantilevered off of there. So we got a 3D shaft and a cantilever problem. This is the bomb, this problem right here. But I'm not going to ask it. But I want to. But I'm not going to. All right, so I can stop recording now. Assuming this actually got recorded. It did. Yay. I'm going to put it on YouTube and let the whole world see it. That's good.
Become a Twitch streamer.
Yeah. So, goodbye, the rest of the world. This is the end of the YouTube video.